So hi everyone, I'm just quickly going to introduce the ODBX, or Open Database of Crystals, implementation of Optimade. So this is a bit different, well, it's very different to Nomad at least, in that we are a very, very small group. We have kind of a much more niche data. And in fact, we didn't have a web interface before Optimade came around at all. So I've kind of been piggybacking off Optimade Python tools to actually make our web interface. So it's developed in the Andrew Morris group. It's now at the University of Birmingham, but was previously at Cambridge. And we mostly focus on high throughput crystal structure prediction. And a lot of our data sort of comes from battery materials, some on encapsulated nanowires, so 1D systems mostly, and also some MOFs. And this sort of work in our group over the last 5 or 6 years, we've got about 1 million geometry optimizations now, so about 50 million force energy configurations. But these are very, very focused on particular chemical systems, so that we don't have this kind of chemical diversity like a lot of these big databases do. Okay, so we have an Optimade implementation. It uses Optimade Python tools, a fairly sort of vanilla version of that, given that I sort of molded the Optimade Python tools to do what I needed to. As I said, it's like an Optimade first database, so we were able to actually construct a separate MongoDB of a subset of our data that is sort of constructed using the actual Optimade Python tools models, which should comply to the spec. So we're very close to 1.0 with Optimade Python tools. There's just a few sort of changes to actual responses and edge cases that we need to add. So at that point, we should basically be at 1.0. It's currently using a very, very reduced set of structures. So I should thank Evgeny for querying TIN in particular, as that's perhaps the one query that would have actually returned answers in that particular case. But hopefully by the end of the week, I'll have some impetus to actually put a few thousand in there from our published work. And we currently do actually have provider-specific fields in our database. These are using extended models from the Optimade Python tools. So you almost certainly can't read it on this slide, but you see these underscore ODBX fields. So for example, just a string representation of the space group, fractional coordinates, all things that we might actually get into Optimade this week, and also some things sort of energies and cell volumes and so on. So generally, the stuff we were just talking about for specifying types and descriptions of these fields would be really helpful, because at the moment in these sort of entry info, all you can do is say that they exist. So the aims for this workshop, I think a lot of the focus, for me at least, will be on the Optimade Python tools, making it as general, useful and usable for people who are maybe coming with new implementations. I just added this sub bullet point about sort of usability of the actual query language, so the filter language. So, I think we could maybe consider wrapping part of the Optimade Python tools library to have a very thin little client for it. So something similar to like np-resta if you've used PyMatGen, which is maybe sort of more motivated towards the use cases people will have for Optimade. With someone else has already mentioned sort of non-equilibrium structures, so not just molecular dynamics, but also configurations from geometry representations to use for machine learning. So that will sort of give us a sort of 50, 100-fold increase in data we can host. And related to provider fields, so if we can have a nice way in the specification to allow for people to sort of link provider fields between implementations, so providing some sort of shared schema, I think that would be a way forward, so we avoid just everyone having a copy of an energy. These may end up being not interoperable, but deciding which ones are interoperable I think would be useful. And I don't really know how we can do that in specification, but it'd be good to talk about it. And then finally, so I think we should maybe focus more on specific use cases in this workshop. So I know at the moment in the paper, we just sort of discuss sodium chloride in a very simple example, which is great to show things actually work. But thinking about how the specification or how the filter language actually works for sort of real world use cases. And hopefully some people at this workshop will have some of those that we can try out and sort of try and break stuff. So I think that's everything from me. Thank you for listening.